Hi everyone, welcome back to the Bioinformatics Coach channel. In today's video, I'm going to show you how you can identify somatic and germline variants using the tool varscan. We are going to use a tumor normal sample pair for this exercise. And let me also say that the ebook as well as the script for this tutorial are all available on my Patreon channel. So check the description box for the link and then you can use that to get the materials. So take note of that. These are the activities we will perform. We will first install the tools that we will use for this exercise. We are going to use Anaconda to do this. And then we will download the example data. We are going to use paired end FASTQ reads. We will also download the reference genome or the reference sequence. And then we will assess the quality of the reads that we downloaded. We will then trim the reads and map the trimmed reads to the reference sequence. After mapping, we will generate BAM files. These BAM files will be processed further so that at the end of the day, we have reads that are of high quality and we will use those reads to call the variants. After variant calling has been done, VCF files will be generated. We are going to process these VCF files further. After that, we will perform some basic statistics on the final VCF that has been generated. And we are also going to filter the variants. So make sure you stay tuned. Before you reproduce this tutorial, you need to make sure your PC satisfies these requirements. You need to have at least 8 GB of RAM. And you should also have at least 8 cores on your PC. For the software, you need to have Linux or Mac OS because the software that we are going to use, especially those for processing the raw reads, they work only in Unix-like operating systems. So Linux or Mac OS will be fine. You should also have Anaconda installed. We are going to use Anaconda to install all the needed tools. I have tutorials that show how to install Anaconda in Linux and Mac OS environments. So make sure you watch those videos. The links to those videos are in the description box. In addition, you should have R and RStudio installed. We are going to use R to generate some plots. In other words, we are going to use R to visualize the statistics results that we will obtain. I have tutorials that show how to install R and RStudio. So in those tutorials, I show how to set up R and RStudio in Linux and Mac OS environment. So check the description box and you'll find the links to those videos. Without further ado, let's start the exercise. This tutorial was prepared using materials from the Galaxy platform. This is the page and I will leave the link to this page in the description box. In this video, I am going to reproduce step 1 up to step 4. Step 5, I am currently working on it, and when it's ready, I will also upload. So make sure you come back to this channel to check it out. And I've also combined some of the activities into scripts. And so when I am executing the scripts, I will explain the codes to you. The scripts are available on one of my GitHub repos. So let's go and then check that out. This is the page and I will leave the link to this page in the description box. When you are here, search for scripts.zip. This file here, it has all the scripts. To download, click it, and then you'll be sent to another page. Look for the download button, which will be on the right side. And then you can click it to download. So click it, and then you can save it in an appropriate location. Alternatively, you can download using the command line. That is what I'll do. So to download on your terminal, just make sure you move the cursor to the download button and then right click it and then get the link. Okay, the download link. So just copy the link and then go to the terminal. So let's go to the terminal and I'll show you how it's done. On the terminal, I'll first create a directory. So I'll say make the variant calling. And then I'll cd into it. Perfect. I'll then use wget to download that zip file. So I'll say wget and then I'll supply it with a download link. I am currently on a Linux system, so this is how I will download it. Okay, it has been done. So if you do an ls, you will see this file there. Okay, that is what we are going to use. You can also use curl to download. If you are using a macOS system, I will recommend you use curl to download. So let me show you how you can use curl to download it. Okay, so in a macOS system, you use curl. So you say curl -- location -- remote name, and then you supply it with a link, and then you execute it. So this will download the file for you. So if you do an ls, you will see in there. This is the file. So that's about it. Now I will switch to my Linux terminal. Let me clear the screen first. Okay. I will now extract the content of this zip file. So I'll say unzip, and then I'll specify the file name. So this will extract the content for me. So do an ls and you find the files there. Okay. All those files with .sh extensions are bash scripts. Therefore, I'll have to add execution rights. So I'll say chmod +x star.sh. So that has been done. Perfect. The next thing I'll do is to install the tool that I'll use for this exercise. But before that, let's clear the screen and do an ls to check the files again. Perfect. So I repeat, the next thing I'll do is to install the tools that I'll use for this exercise. I am going to use Anaconda, and I assume you also have Anaconda installed. So let's proceed. We need to first add channels. So let's do that. Before we proceed, let me say that I have tutorials that show you how to install Anaconda in Linux and macOS systems. So make sure you check those videos out and then set up your PC. Now let's proceed. We will add the Conda channels. So I'll say conda config add channels. I'll add the first one, which is conda forge. I'll add a second channel, conda config add channels, and that is bioinconda. Okay, that has also been done. I'll now install the tools. Because I have a couple of tools, I have prepared another file, which is the environment.yml file. This file has instructions that Conda will use to set up my environments. So let's display the contents, and then I'll use that to explain some few stuffs. So cat environment.yml. And so this is what I have. This is the contents. Okay, so this is just a text file with this extension. Okay, so I have name. So this will be the name of the environment. It's called variants. And I have channels. So these channels are the ones Conda will use to search the tools and then install them. And I have the tools that I want to install. So that's about it. So I'll execute a command here to set up my system. So let's proceed. So I will say conda env creates -f, and I'll specify the file here. So let's run this command. Okay, the tools have been installed. And so you will have this message here. To activate this environment, use conda activate variants. To deactivate, use this. Okay, this is because the name of the environment I specified in the file was variant. So let's look at that. We are going to test. So let's proceed. So let's first activate the environment. So I'll say conda activate variants. And then I'll test some of the tools. So let's say some tools. Perfect. That is also done. Okay. So that's about it. I assume that the rest of the tools are also working. So we are ready to go. So let's proceed. Let's go back to the Galaxy tutorial. I mean the original tutorial, and see what is there. So on the Galaxy page, you will see that the first step is data preparation, and that means we are going to get the data. Okay, so if you go there, the links are available here. Okay, you can use that to download the data. But then I have prepared a script that will do the download. So let's use that script to download the data. We are going to download the FASTQ files and also the reference sequence. Everything is in the script. So let's go and then check it out. Okay, so let's do an ls first. This is the script that will download the data for us. So let's download the data. So I'll say /download data.sh. So this will download the data for us. So let's do that. So let's wait for the download to complete. Okay, the data has been downloaded. Let's check them out. So do an ls and you will see a new directory called data. So let's ls into it. And then you find a directory called FASTQ. This has the raw reads, and there's also a directory called ref. This has the reference sequence, and this is an adapter, a sequence adapter. We are going to use this to trim the reads. So let's ls into the FASTQ. So we say data /FASTQ, and you find another directory called raw reads. So let's ls into that, and you find a file there. So we have a tumor normal sample pair. So we have, there's a normal, there's a tumor, and we also have the reference sequence. So let's say ls data /ref, and you have the sequence there. So there, and we also have the true-seq adapter. Okay, so this is the adapter we will use to trim our reads. So we have the data. We have also installed the tool, so we are ready to go. So let's proceed. We will now perform quality control. So let's look at the Galaxy tutorial, and then we will know what kind of QC we should do. So let's go to the browser. Okay, so let's scroll down to quality control. Okay, so with the quality control, we are going to inspect the quality of the reads. Okay, and to do that, we will run fastqc. That is what has been stated here. We will run fastqc on all the 4 FASTQ files, and after that, we will aggregate the results using multi-QC. That will be the first quality control we will do. So let's go and then do that. So we will run fastqc. So we say fastqc data /fastq /raw reads *fastq.gz. So fastqc will start the analysis and then give us the results. We are going to have 4 outputs because we have paired and reads. And so for each sample, there are 2 FASTQ files. So that means 2 outputs will be given for each sample. That gives us 4. So let's wait for FastQC to finish the analysis. Okay, FastQC has finished the analysis. Let's check the outputs. So do an ls data FastQ raw reads, and you find this and then this for each FastQ file. So these are the FastQC outputs. We are going to aggregate all these results into a single HTML file. So we'll use multiqc. So we say multiqc data slash FastQ slash raw reads star underscore FastQC star, and then we run it. So multiqc will aggregate all the results and then put them in a single file for us. So this will make it easy for us to check the results and also compare. So let's check it out. MultiQC has finished its work. So if you do an ls, you will find a file called multiqc underscore reports.html. So this file has been generated. We also have this one, but we are going to view just this one. So let's do that. Okay, so I'll open this report, this file here, using my browser. So let me do that now. Okay, so this is the file. I'll open it. Okay, so it's open that, so you can select any of the samples and then view its reports. So let's check. Okay, so let's scroll down. Let's look at the sequence quality histogram. So that's what we are. So looking at the plot here, you will see that the main quality scores are all within this range. FastQC generates results, okay, and these results can have one of 3 colors. Okay, so if it's green, then that means that everything is okay, the quality scores are high. And we can see that all the samples here, okay, they are within this region, which is green. That means high quality scores. And so this indicates that the reads are of good quality. That's what I will say here. But then if you look at the Galaxy page, it also highlights another point here. Let's check the points. So it's, yeah, so that's point number 2. It's asking which aspect of the quality report is most puzzling to you. Okay, it hints at the GC contents of the reads. So let's check the GC contents. That should be here. So there's what it's referring to. So if you check the documentation here, it says that what we have is a multimodal distribution, okay, which is a non-normal distribution. Yeah, so what we see is that the plot here is bimodal, okay. So with the GC content, we expect to see a normal distribution, but here it's shown bimodal. And so when we come here, it tells us that bimodal distribution is a characteristic of the ESOM sequencing capture method. That's what it tells us. So that means that the data we are dealing with are ESOMs. Okay, they are ESOMs, and that is why we have this bimodal distribution. Okay. And then the Galaxy tutorial also tells us to apply retrimming and filtering to see if we can improve the data. We are going to use Geomatic to do this. I have prepared a script that we use for the trimming. Okay, so in the script, I made sure to include all these options that have been stated here. So let's go back to the terminal and then continue. We are going to use this script called trimreach.sh. you can use the cat command to display the contents. I have specified 8 threads, but if you have a higher computing power, then you can increase this number. Okay, so take note of that. But if you have 8 threads, you can still use it. So let's continue. I'll execute that script and then the trimming will be done. So I'll call it and then I'll run it. So let's wait for the trimming to be done. Okay, the trimming has been done. So let's check the files. The files will be located in the data directory. So let's do an ls into it. Data/Pascal. And you'll find this directory. So this has the data that has been generated. So let's ls into that as well. Okay, so this is what we have. We are going to have the forward and the reverse for each of the samples, and we're also going to get unpaired. So these are reads without mate pairs, but we will use the paired ones. Okay, so R1, R2, these are the files that we are going to use. So according to the Galaxy tutorials, we also have to do a QC. We have to inspect the quality of these reads, the new reads that have been generated. Okay, so let's do that. Let's even check the page first. So if you check, it says we have to use fastqc and then multiqc again. Okay, and then there's also a question here: how did read trimming affect the quality reports? So let's generate the report first and then we will discuss. So we will say fastqc and we say data/Pascal/trimmed reads and we say star.fascal.gz. And notice what I have here. I said trimmed. Okay, so I gave, in addition to the names, the original names, I also added this one, trimmed. Okay, I always try to use a naming convention so that I have a brief description of what these files are. Okay, so it's to describe the file so that I will know what treatment I have given the files or what processing I have done. So because I have trimmed, that means that these are trimmed. That's what you need to know. So I'm going to run fastqc and then use multiqc to aggregate the results. So I'll run this. So let's wait for fastqc to also finish the analysis. Okay, fastqc has done its job. We are now going to run multiqc. So we say multiqc and then we specify our files star_fastqc star. So let's run this. Okay, report has been generated, and so we have this name here that has been generated. Okay, we have multiqc report 1, multiqc data 1. This is because we already have a multiqc report, okay, with the same name, multiqc reports. That was for the raw data. Okay, but because we are now performing a new QC, okay, on the trim data, multiqc has given it 1, okay, so that we don't overwrite the existing data. So we are going to view this HTML file. So let's do that. Let's even check it here first. So if you do an ls, you'll find it's here. So this and then this, these are the new reports. So we'll view them using our browser. So let's do that. Okay, so let's view this file. It's open now. So let's check. We'll use the sequence quality histograms again. Galaxy documents. So let's look at the quality here. So the quality here is also good. But then if you compare what we have, this is for the trimmed reads. If you compare that to the raw data, there hasn't really been a vast improvement in quality. And this is also stated here on the original documents. Okay, that the tutorial that I'm using, it says what? The trimming did not have any substantial impact on the average. Okay, there was only a small fraction of successful adapter removal, and that is visible. So I think that's the only thing that has changed, okay, in the trim data. So let's even check that out. So there's the adapter content here. Let's check the original one. Now look at this here, and then look at this. So that is the change that has occurred. Okay, there has been some adapters. There has been some adapters being removed. That is the only change here. But the quality itself, there hasn't really been a vast improvement. It's still the same or almost the same. They are similar. So that is what the Galaxy tutorial tells us, and we have also observed that here. So that's about it. So let's proceed. The next activity is read mapping. Here we are going to map the reads to the reference genome. We are going to use the tool BWA. We are going to use the trimmed reads, i.e. the output of Somatic. And I have prepared a script that has all the commands that we will use for the mapping. So let's go and then check that script out. This is the script that we use, map reads.sh. Let's take a look at the contents. So I will display it here. Okay, so I have my reference sequence here. I have specified it here. I have also indicated the number of threads, 8. You can increase this number if you have more CPU cores. Before mapping, we also need to index the reference genome. So I have a command here to help me do that. And then I use a for loop to iterate over the samples and then map them. Okay, I am dealing with more than one sample, so it's much better if I use a for loop, and then that will help me to streamline things. When mapping, we also need to indicate read groups. Okay, that is done here. Okay, so with the read groups, we need to specify the sample ID and sample name. Okay, I am using what has been given in the Galaxy platform tutorial, so I'll use those numbers, and that is what I have stated here. So for the normal sample, we use an ID of 2313335, and then the sample name is normal. And then for the tumor, we use this and then this. Okay, for the sample ID and then the sample name. Using the for loop is very important, okay, especially if you are dealing with lots of samples. And for those who want to learn more about how to use loops to process lots of samples, you can also reach out to me. My email is in the description box, so take note of that. And I also have my read 1, read 2 for each of the samples. So there's the scripts. So I'll execute the scripts to map the reads to the reference genome. So let's do that. Let's clear the screen first. So I'll say .map /map reads.sh, and so indexing will start, and then the mapping will also follow. Okay, mapping has been done. So let's check the files. If you do an ls, you'll find a directory called bams. Okay, so let's ls into that directory and we will see two files here, one for the normal sample and one for the tumor sample. So I have them named as normal.raw.bam and then tumor.raw.bam. Okay, I use the raw here because these BAM files are going to be processed. Okay, we are going to process them further and then get some new BAM files. Okay, so let's proceed. So let's look at the next activity. Let's go back to the Galaxy platform. On the Galaxy platform, the next activity is to process the mapped reads. So here is titled mapped reads post processing. And so here, there are a number of activities here. We have to filter based on read properties. We also have to remove duplicates. We have to left align reads. We have to recalibrate the read mapping qualities. And then we also need to refilter the reads based on mapping quality. Okay, so all these activities, I have combined them into a single script. Okay, so that once you execute the script, all of these steps will be done. Okay, so we are going to execute that script and then get our final BAM file. So let's go back and then check the scripts. And so the script for processing the map reads is here. This is the script. And so if you display the contents, you'll find the commands there. And then I have also given comments. Let's check here. I've also given comments that will help you to get information about what each command is doing. So let's look at that. So we are going to execute the script and then get our final BAM file. So let's check it out. So I'll say ./process bams.sh and then I'll run it. And so the activities are going to be performed. This will take some time, so just wait and then later check the outputs. Okay, the processing of the BAM files has been completed. So let's take a look at the output files. So let's clear the screen. Let's do an ls. We are going to check the BAM's directory. So this has the files we will need, the final BAM file. So let's ls into the BAM's directory. And we are going to find lots of BAM files. So the files that are of interest now, the ones that we are going to use for the variant calling are the normal.final.bam and then tumor.final.bam. Okay, so we started by processing the raw.bam. Let's just do an ls. So ls bams slash star.raw.bam. Okay, these were the ones that we generated after the mapping. So these ones were processed. Okay, the processing was done, and then we now got this one. Let's do ls bam slash star.final.bam, and then we got these two files. So these are the ones that we are going to use. All other files are intermediate files, which we don't need now. Okay, so you can choose to remove those ones, or you can choose to leave them. I decided to leave them because I thought maybe some of you viewers may want to explore these files further, so I decided not to remove them. So you can choose to leave them or you can choose to remove them from your PC. That's fine. But what we want is this and then this ones, and then you can also leave the normal .raw and then the tumor.raw. These are the raw BAM files. So this and this, you can leave them. Okay, that's what you need to know. So we'll continue. We are now going to call the variants and we are going to use the final.bam files. So let's do that now. So I'll do an ls first and then I'll proceed. So with the variant calling, we are going to use the script call underscore variant.sh. So this has the commands we are going to use. So let me just display the commands. So I'm using the cat command to display the commands. So what this script will do is that it is going to execute a series of commands starting from here up to here. So that's what will happen. A pileup file will first be generated. Okay, I repeat. First, a pileup file will be generated. And after that, varscan will use the pileup file to call the variant. So varscan will identify somatic and germline variants as well as LOH events. LOH stands for loss of heterozygosity. After varscan has completed its work, two files will be generated, one for SNPs and one for indels. These are the files. So these files will be processed, and after that, they will be merged. So we will have three files, one for SNPs, one for indels, and then a third file which is a merged file. So the merged file contains both SNPs and the indels. So that is what we are going to do now. So let's clear the screen and then execute the script. So I'll just do an ls again to check the files, and I will call the script. So I'll say /call underscore variants. Okay, so the variants are now being called. So let's wait for everything to get done for us. This activity took about 25 minutes when I ran it. So you should expect the same. Okay, variant calling has been completed. So after varscan has identified the variants, it also displays a report file. So this is more like a summary to let us know what happened. So for now, I want us to focus on these ones. Varscan, after identifying the variants, also lets us know the types. Okay, so if you take a look at the documentation, let's just go back to this page. I'll leave the link to this page in the description box. So this is the somatic mutation calling page. So if you scroll down a bit, you will find some information here. So let's look at this table, the output section. So we specified the output format to be VCF. So we will look at this side here, this section. Okay, so let's look at the somatic status, that's SS. So for each record or for each variant that varscan identifies, it labels that record for us. So it will let us know if that record is germline, somatic, LOH, or known. And that is what has been given here. Okay, so each of these is given a number. So it is that number that we will use to identify the various types of variants. We will look at that very soon. So let's go back. So the somatic status code, that's the variant types. That is what has been given here in the summary. So we have germline, LOH, somatic, unknown. And then we also have their respective numbers. Okay. Of course, these are the raw variants. So we are going to do some filtering and then we will get the final numbers. That's when we get to the statistics parts. Okay, so now let's continue. So let's clear the screen and then continue. Okay, so now let's do an ls. We are going to find a directory called variants. This directory has the output file. So let's ls into it. So I'll say ls variants, and I'm going to see all these files. Varscan generates a separate file for SNPs and a separate file for indels. Okay, so these are the two files, but I decided to merge these two files into a single file, and that is what is here. Okay, variant.org.vc.gz. So this file here comprises of the indels and then the SNPs. So depend on your objective, you can decide to analyze the SNP file or the indel file, or you can decide to mesh and get a final file which you use for downstream analysis. For this tutorial, I'm going to use the merge one, which is the variant.org.vc.gz. Okay, so I'll start with some exploration. I'll begin by getting the sample names. Okay, I'm going to use BCF2 to do this. So first of all, let me cd into the variant directory. So I'll say cd variants. I can decide to do an ls again, that's fine. So to get the sample names or sample IDs from a VCF file using BCF tools, we say BCF tools query -l, and then you specify the VCF file. So here it's going to be variants.or.vcf.gz. And this is going to display the sample names or sample IDs for you. So we have normal and then tumor. So everything is looking good. Now let's continue. I'm going to do an ls again to look at the files. Perfect. Okay, what we are going to do next is to filter the variants. So we are going to select all variants that pass the filters. So to do that, we will consider this column. Let me just issue this command. So I'll say zgrep, then I'll specify this. I'll specify variant.or.vcf.gz. I'll say ~n. You can use another way to get the headers, it's fine. So this column is what we are going to consider. So this filter column, so if a variant pass the filters, then its value is going to be pass, PASS. Okay, so that's what we are going to use to filter the variants. So to filter the variants based on the filter column using BCF tools, we will say BCF tools, and we say filter, and we say -i. So -i here indicates that we want to include those records that satisfies the criteria. So we will put it in quotes, that's the expression. So I'll say filter equals, and then the pass, we put it in double quotes. So that's what we are going to. So that means that all records where the column filter, okay, the value there is pass, should be selected. That is what the -i here is for, include. Perfect. So now we are going to specify our VCF file. That is this one here. And then we say -o z, then -o. So I'll say variant.or.pass.vcf.gz. That's the name I'll give it. So let's execute this command. Perfect, that has been done. So let's do an ls, and we are going to find that file there, which is this one here, variants.or.pass.vcf.gz. So you also notice that I give some suffix for each of these files. So this lets me know what has been done to the VCF file. So here I had variants.or.vcf.gz. Here I have variants.or.pass.vcf.gz. So this pass here lets me know that these are variants that passed the filter, okay, or the criteria that I used. So I am going to index the variants.or.pass.vcf.gz. So I'll say BCF tools index variants.or.pass.vcf.gz. Perfect, that has been done. So it has been executed successfully for us. Okay, now what we are going to do next is to extract the variant that we identified in the tumor sample. Okay, remember we had normal and then the tumor, but I want to focus on the tumor sample. So I will need to extract the variants or subset the variants that have been identified in the tumor sample. Okay, so we are going to use BCF2 to do this. So to select variants that are present in a particular sample in a multi-sample VCF using BCF tools, we use this command. So we say BCF tools view, and then we say -s to specify the sample. So here the sample is what? Tumor. And then I'll say variants.or.parse.vcf.gz. And then I also need to indicate this options -c1. So this lets me select the true variants. Okay, the true variants that have been identified in that particular sample. That is this one here. So that is what I have. And I'll say -oz-o, and I'll say tumor.vcf.gz. So I'll execute this command to subset the variants. Perfect, that has been done. So let's do an ls. We are going to find the tumor.vcf.gz. Now I'm going to index this VCF. So I'll say VCF tools index. Now I'll say tumor.vcf.gz. So I'll execute this command. Perfect, that has also been done. So now we can continue. So let's clear the screen. Let's do an ls again and then proceed. Okay, we are now going to perform some statistics. We will begin by getting the number of variants that are in the tumor sample. Okay, so we are going to use a Linus command to do this. So to identify the number of variants in a VCF file using a Linus command, you will say zgrep. This is what we are going to use. And by the way, I have covered a separate tutorial on this. So if you are interested, you can check the description box for that video. I'm using one of the 4 commands that I use in that video. So let me just go over again. Let me just start. So we are going to use a Linus command to count the number of variants in this VCF file. So we will say zgrep-v-c, then I'll specify a pattern here. Then I'll indicate that VCF file. So let's execute this command. Perfect. So this will give us the total number of variants. So that's what we have here. So that's the total. So this total here is what? It's the total of all the variant types that I showed earlier on when we visited the varscan page. Okay. Now let's take a look at the SNPs and index. We are going to count the number of SNPs and indels. So I will start with the SNPs. So to count the number of SNPs in a VCF file using BCF tools, we will say BCF tools view, and we say -v, and we say SNPs. Then we indicate the VCF file, and then we issue our grep command. So grep-v-c, and then we specify our pattern. So let's execute this command. Perfect. So this will give us the number of SNPs. We can do same for indels. So what we do is that we are going to use the same command, but then we are going to change the SNPs here to indels. So let's do that. So to count the number of indels in a VCF file, using BCF tools, we say BCF tools view -v indels, and we say tumor.vcf.gz, and then we issue our grep command, then we indicate our pattern, then we execute. So this will give us the number of indels. Okay, so that's it. Please take note that sometimes you may have to add some additional options to get the true variants. Okay, but this time we have already filtered and done all that, so that is why I'm using this one. So this one is okay. Okay, now let's continue. So we have our number of SNPs, we have our number of indels. So these are the respective numbers. Now let's take a look at another statistic. We are going to look at the number of variants per chromosome. Okay, so first of all, let's display the chromosomes, okay, that are in the VCF file. So to display the chromosomes in a VCF file using BCF tools, we say BCF tools, and then we say query -f, and then I'll say percentage, and I'll add my chrome. I'll say /n, and then I'll indicate the VCF file, which is this one, because I want just the chromosomes. I don't want all of them, so I'm going to remove duplicates. So I'll add unique to it. So let's execute this command. Perfect. So this will give us the chromosome. So we have chromosome 5, 12, and 17. Okay. The reference sequence we used was downsampled, so it's only the CHR5, 12, and 17 that are in that reference sequence. So that is why we have these 3 chromosomes. We are using a downsample data. Okay, so let's continue. So we have the chromosome. So now we can get the number of variants for each chromosome. Okay, so we are going to use BCF to do this. So to get the number of variants that have been identified in a particular chromosome using BCF tools, we will use this command. We will start with the chromosome 5. So we can say BCF tools, then we say view, and then we will indicate our regions. So I'll say -- regions, and I'll say CHR5, and then I'll indicate my VCF file, and then I'll issue my grep, and then I'll give my pattern. So this should give me the number of variants on chromosome 5. Perfect. So I have 3707. That is for that chromosome. We can do same for chromosome 12. So this time we just change the 5 to 12, and that will give us chromosome 12. So that is what? 4427. Let's do same for chromosome 17. That's CHR17. And we also have that done also for us. So we have that also here. So we have SNPs index. We also have the variants per chromosome. We have all these values here. Now let's take a look at the other one. So let's go back to the varscan page. We talk about germline, somatic, LOH, or unknown. Okay, so this time what we are going to do is to count the number of variants. Okay, so we are going to get the number of variants that belong to each of these classes. Okay, so we have germline, somatic, LOH, or unknown. So we are going to count the number of germline, somatic, LOH, and then unknown. That's what we are going to do next. So let's go back to the terminal. Let's clear the screen and continue. Let's do an ls again, and then start. So before we do the count, let's take a look at the variant types. So to do that, we issue this command. So I'll say zgrep, and then I'll use this pattern here, and then I'll specify the tumor.vcf.gz. So let's execute this command. So this will give us these lines. So I want us to take a look at this one here, the one here. So we are going to use this line. So we have info. This is the info field, okay, in the VCF. So it says the info field, there is another field called SS. Okay, so the SS has some information. So that's what we are going to use. So we have somatic status of variant. We have 0 equals reference, 1 equals germline, 2 equals somatic, 3 LOH. Then we also have 5, which is unknown. So That means that for the VCF file, these are the values, or these are the codes that we can use to identify the variant types. I repeat, for the VCF file, the numbers here are what we will use to identify the variant types. So let's take a look at the variant types. So we will issue a bcf2 command to do that. I'll do that for us to see. So I'll start. So I'll say bcf2's query-f percentage, and I'll say info/ss/n, and I'll indicate my VCF file. Let's execute this command. So we have this. Okay, now everything has been displayed. Well, we just want the numbers. We want to remove duplicates. So I'll reissue the command again. So I'll first sort, and then I'll say unique. So this should give me the value. So I have 1, 2, 3. Okay. So the 1, 2, 3, let's go back to the command we used to get that info here. So we have 1 for Germline, that is 1. 2 for somatic, that is 2. And then we have 3, that's LOH. And we also have 5 unknowns. So here we have 1, 2, 3. There's no first. That means that the unknowns are not in this VCF file. Of course, we did some filtering, so it's likely those variants have been filtered out. Okay. So that's what we have. So let's go back. So here we just display the variant, but we need to count them. So that's what we are going to do next. So for the counting, that's what we'll do. We will still reissue this command here, and we will add -c to it like this. So let's execute this command. Perfect. So once we issue this command, then we are going to get the numbers, the counts, as well as the variant types. So we have 1 for Germline. So Germline, we have 10787. Somatic, we have 1267. LOH, we have 175. Okay, that's what we have here. So this is another statistic that we can generate from our VCF file. Perfect. So now we've done some statistics. So as the saying goes, a picture is worth 1,000 words. Okay, so visualization helps us to easily interpret and understand our data. So what we are going to do is that we are going to visualize these statistics, the ones that we have generated, these values. We are going to visualize them. So to do that, we are going to use R to do this. So I want you to also open your RStudio, and then we will visualize. So we are going to generate pie charts and then bar charts. So let's continue with that. So let's open our RStudio now. I'll open mine here. Okay, so I have opened my RStudio. So I'll open a new script. Perfect. So I have that done. So there's now time for the analysis or the visualization. Let me put it that way. So with the visualization, I'll start with the SNPs and indels. So I will generate a pie chart to visualize the number of SNPs and indels. So let me first give a comment here. So I'll say pie chart of the number of SNPs and indels. Perfect. Now I am going to continue. So with the pie chart, you will need values. Okay, so let's first get our values. So I will say counts, and then I'll specify or indicate the number of SNPs and indels. I'll start with the SNPs. So I have that here. So the number of SNPs, we got 10177. And then for indels, we got 2052. So I have that done. We will also need labels. So I'll say labels, and then I'll specify SNPs, indels. these will be our labels. We also need colors. So I'll just say colors. And for colors, I'll use red and then blue. Perfect. Now I am going to generate the pie chart. So I'll call the pie function. So I'll say pie, and then I specify my counts. That's the values. Labels equals labels, and then main. So main is the title of the plots. So main is going to be equals to variant counts, and I'll say snips and index. And then I'll specify my colors. So I'll say col equals colors. So this is the code. Now let's execute the script. Perfect. So we have the pie charts being drawn for us. And by the way, I have a separate tutorial on pie chart. So if you want a detailed explanation of how to generate pie charts using R, then you can watch that tutorial. The link to that video is in the description box. Perfect. So we have visualized some of the data or some of the information. Perfect. Now let's continue. We are now going to look at the variants per chromosome. So that will also be here. So I'll say for that one, we are going to use a bar chart. So I'll say bar chart of, let's say, number of variants per chromosome. Now let's generate the bar chart. So for the bar chart, you still need your values. I'll still use the variable count, but you can use a different name. It's also fine. So I'll say counts, then I'll specify. So for chromosome 5, it was 3707. Chromosome 12 was what? 4427. Chromosome 17 was 4095. So I have the counts. Now we need labels. So here, the labels are going to be the chromosome names. Okay, so you have CHR5, CHR12, and then CHR17. Make sure they are all in quotes, single quotes or double quotes. So I have the labels. Now let's continue. So here we will call bar plots. So I'll say bar plots, and I'll say counts, and I'll say main equals variant counts per chromosome. And then I'll say names.arg equals labels. And then for the x axis, that's the labels, I'll say x lab equals, and I'll say chromosomes. You can say chromosome or chromosome. That one, it depends on what you want to put there. So for now, I'll just use chromosomes. And then for the y lab, that's the y-axis label. That's y lab. Lab equals to variant counts. Let me format this. I'll send this to another line. Perfect. So this is okay. So now let's execute this command. Perfect. So we have that also generated. So there's the bar chart. Now it's possible to change the colors here. So let's take a look at something here. I'll just generate another one here. So I will define a color or colors. Let's first use colors. So I'll say colors. Let me just do this just to let you know that you can change the colors. So I can say red, blue, green. So if I define this color, then I need to add that information when plotting. I can say COL equals colors. So let's execute this command. Perfect. So now we have the colors displayed for us. So we have each chromosome and its color. So chromosome 5, chromosome 12, chromosome 17, they all have their respective colors. You can also use the same color. So if, let's say, we want to use blue, let me just define it here. So I say colors, say rep blue 3. I just want to repeat the blue text here 3 times. Then when I come to the command, I'll indicate the colors. So I'll say COL equals colors. So let's execute this command. Perfect. So we have that also done. So we have generated a bar chart with different colors. Okay. So that's how we generate bar chart. And I'm also going to make a separate tutorial where I go into details with how to generate bar plots or bar charts. Okay. So if I finish that tutorial, I'll also leave that link in the description box for you to check. So that's going to be a future tutorial. Okay, so we have the bar charts also done. Now let's take a look at the germline, somatic, and then the LOH events. So let's do that also here. So I have, I say pie chart of germline, somatic, and LOH. Let me make this one's uppercase. Okay, so for that one too, you need to specify the values. So I'll do that here. So I'll define my counts. I have counts again. I have germline was 10787. Somatic was 1267. And then we have LOH, that's 175. That is done. Labels, you have germline, somatic, LOH. That is also done. And then colors, I will define them again. I have red, blue, green. We have defined them as well. So now we are going to generate the pie chart. So it's the same command here, okay, as this one here, but just that the title will change. So we say pie, and then we have our counts, labels equals labels, main equals what? Germline, somatic, LOH. Let's use this title. And then for colors, what's colors? So let's execute this command. Perfect. So we have that also done. So if you even look at this, once you have visualization, it lets you easily understand the data or the information that is being presented, like the ones we have done so far. So these are things that you can do after you have identified your variants. So with the pie charts, you can also generate 3D pie charts. That is something that I have covered in another tutorial. So just check the description box, you'll find a link to that video as well. So these are some of the statistics that you can generate after you have identified your variants, and we have done that here. So now let's get back to the command line and then continue. Okay, so let's clear the screen and do an ls and look at the files. So we have our files here. So far we have been able to identify somatic and germline variants, and we have also been able to do some statistics. Another thing you can do is to annotate your variants. So if you take a look at the Galaxy tutorial, there's a part where it shows how to annotate variants. So we have that here. That's section 6, variants, annotation, and reporting. So that is here. So for this section, I'm going to cover it in another tutorial. I'm currently preparing the material, so once I'm done, I'll make a tutorial on that. For the annotation, there are a couple of tools you can use. You can use ANOVA, you can use Snip EFF, you can use VEP. There are a number of tools available to do that. And so I'm going to prepare some tutorials on the variant annotation, and then I'll also let you know if that tutorial is uploaded. So just make sure to come back to this channel and then watch that tutorial. So that'll be all for this tutorial. And if you want the scripts, if you want the ebook for this tutorial, just check the description box. You'll find the link to the ebook. So the ebook, all the codes have been given in the book, and then you also have some explanation. So it makes life easier. So instead of typing everything, you can just look at the codes and then just either copy and paste or just retype everything and then just learn something new. That's what I'll say. So just make sure to come back to this channel as I'll be making more content. And so that'll be all for this tutorial, and I'll see you in the next session.